So you might have heard that there's a lot of effort, especially DARPA, are funding a huge research program in computing on encrypted data. So this is the idea: is you encrypt data and you want to compute on it, and there's different ways of doing that. So one way is to use this mega thing called Fully Homomorphic Encryption, which you might have heard of, which you might also think is completely impractical. And I would kind of agree with you, but I'm going to kind of convince you it might not be too impractical at some point. And the other way of doing it is with multi-party computation. So what I'm going to do in this talk is show you can do both together and get efficiency improvements over the state of the art. So I have two sort of what ifs, just to kind of give you an idea of what we would like to do in about 30 or 40 years' time, or by the time I've retired or something. We've got two drug companies, each has a database of molecules and toxicology test results, and they want to combine their results. So they want to know, I've got drug A, I want to know, did drug A kill someone when it was used by drug company B, or did it kill the rat or whatever? And so they just want to get the yes-no answer without revealing what drug they're testing. Okay, this is apparently, we've talked to a bunch of drug companies in the UK, and this is a big thing they want to do. Yeah, they want to, so they don't have to keep replicating. They might have done the tests for different reasons. One might have been trying to solve cancer, one might have been trying to solve Alzheimer's, but they still want to have the toxicology results of sharing chemicals. And so that's one application. You can imagine you encrypt the databases and you want to do some sort of comparison on them. Another one is if you have network traffic and the government or some agency wants to search the traffic for some anomalous behavior, but the network operator doesn't want to give this information away to the government, and the government doesn't want to reveal exactly what it's searching for, but you still want an outcome to know what's going on. So basically, think of some examples where you encrypt stuff and you've got private stuff and you want to search it, or you want to perform some operation on it. The classic example, which I haven't put in the slides, is the one that's actually deployed is in Denmark. They have a sugar beet. They make sugar beet and they have to sell the sugar beet, and there's there's a monopoly of sugar beet suppliers and there's a monopoly of sugar beet purchasers, and they want to determine the clearing price of the sugar beet every year. Weird, but apparently it's Denmark. Yeah, they don't have high-tech industry, so they just do sugar beet. This is videoed. Whoops. Denmark's a really nice place. So yeah, they also. So they actually run a sugar beet auction using multi-party computation. They actually encrypt the auction, the amount they want to buy and sell, and then they execute a protocol to work out what the clearing price is. This is done every year, and there's actually a spin-out company of the University of Aarhus which do that. Okay, so there are two main ways of performing computations on encrypted data. Now, the first one that everyone's probably heard of is fully homomorphic encryption. So this was invented by, the idea was invented by Rivest and some others back in 1978, but actually being able to do it in theory was first by Craig Gentry in 2009. Okay, the idea is that party A encrypts some data, sends it to party B. Party B does some computation on that data, sends it back, sends the result of the computation, the encrypted result of the computation back to party A, and then party A decrypts. Okay, and this is slightly impractical for general computations, but we can now actually do this for small computations, and there's some recent work of Stanford and IBM where they actually implement this for some very simple database queries on some relatively small databases, but you can do real computation with this. The other approach is what's called multi-party computation, and that was developed around the mid-1980s, mainly used as a theoretical tool. And here what happens is that you have many parties in a computation, and they all have their own input, and they want to keep their input secret, but we want to compute some joint function of the inputs. Okay. Towards the end of the talk, I'll have a much more concrete application scenario. And then what you do is they want to compute this function, but they want to they want no information about their revealed input. So the classic prototypical example here is voting. Yeah, you all have who you're voting for. You want to know the outcome of the election, but you don't want any information about the what your vote was, except for what you can determine by the outcome of the election. Yeah. So, for example, if everybody in the room were in Google, yeah, so everybody in the room, say, voted Democrat bar one person, okay, and that one person, then there was 100 people voted for Democrat, and then one voted for Republican, and then the result came out. You know, you would kind of, you know, you were the one Republican. You would know that everybody else was a Democrat. Yeah, it's just, you could just compute. What you can compute about the inputs is what you could get from the outcome, but nothing else. Okay. So in theory, both technologies can compute anything. Everything's a done deal. It's polynomial time overhead. It's a polynomial overhead. Everything's fine, and we can all go home. Okay. But there's a big difference between theory and practice. So in fully homomorphic encryption, the overhead, although polynomial, is a huge cost. Yeah, absolutely huge. The constant is massive. But the benefit is there's zero communication cost. Yeah, I just send the stuff to the guy does the computation, he sends the stuff back, and that's nice and simple. In multi-party computation, we have virtually no computational cost, a small overhead compared to what we would do in computing the thing in the clear, in some weird computing model, but still virtually no computational costs. But the communication cost gets very high, so we kind of pay in different ways. And we can make any technology error tolerance. That means in the sense that if the parties are malicious and want to disrupt the computation, we can protect against that, okay? Right. So as I said, FHE is currently impractical for all but the simplest functions. You can't take your terabyte database or exabyte database and do an encrypted search on it. That's out of the question. Although you can still do some useful things. And as I say, MPC has been deployed for some operations. There's this Danish sugar beet auction. SAP has a supply chain management solution where they can, different people in the supply chain can put their inputs in. It will compute the optimal supply chain without revealing information. So FHE is impractical, but MPC has been deployed. It's been deployed for the sugar beet auction. I was talking about SAP with the supply chain management. And there's one other example which doesn't spit to my mind at the moment, but there's meant to be 3 examples. But yes, there's an Estonian company called Cybernetica, which has deployed a solution which amalgamates financial data from different small startups to get aggregate financial information from those companies. The thing is that everything that has been deployed in the real world, those 3 applications and everything that's been implemented as experimental systems, essentially only works against what's called semi-honest adversaries. There are adversaries that are allowed to listen into the protocol and try and work out information. So if we go back to the voting example, they try to break the privacy of the votes, but they don't tolerate adversaries that are trying to disrupt the election or to disrupt the computation. Yeah. So what we would like is to protect against adversaries that can do arbitrary computation and just want to completely screw over everybody else, okay? And the other thing that they require is that for all the implemented systems up to this talk, you can only have 3 people in the computation, of which at most 1 can be bad, okay? So you can only tolerate 1 bad guy out of 3. Okay, so what I'm going to show is so for the next few slides I'm going to give a bit of maths, and I'm going to show, very moronic actually, we're going to show how to combine fully homomorphic encryption and multi-party computation together to get something that's actually much better and more practical. Okay, we can tolerate as many parties as we want, 2 or more parties, if we have n parties, n minus 1 of them can be corrupt, and they can execute any possible corruption. They can try and disrupt the protocol any way they want, and we'll detect when they disrupt the protocol, and we can abort the computation rather than get the invalid election result or the invalid outcome of the auction or whatever.
Can the bad guys collaborate?
And the bad guys can collaborate. So as bad as you want, basically. Okay. Okay, so To say this, the underlying crypto is really simple. It makes, if you understand the RSA crypto system, this is easy, much easier than the RSA crypto system. We teach this kind of to the kind of bare bones of this to first-year undergraduate computer scientists. So this is really moronic. Okay. So we assume there's n parties, of which n minus 1 are bad guys, and they assume there's some global secret key alpha, okay, which is an integer mod p. And but we don't actually know what it is. What it is that party 1 generates a random alpha 1, party 2 generates a random alpha 2, and this global secret, which is secret, is just defined to be formally the sum of the random numbers that they've all chosen. Okay, so that's the kind of setup. And then what we're going to do is we're going to secret share the data. So every piece of data item within the computation is going to be shared in roughly the same way. So if I have a data value x, it's going to be shared with the parties as follows. Everybody's going to have a value xi, such that the sum of the xi is equal to x. If there's two parties, I've got x1, you've got x2, and the x is x1 plus x2. And we also hold, each party holds a share of a MAC, a message authentication code, on that particular value x. So, but the MAC is just purely alpha, that's secret from the previous slide, times x, and we share it out. So I have gamma 1, you have gamma 2, and together we have a MAC. And the idea of the MAC is that this is going to check that we haven't done anything wrong. Okay, so this is the actual data, and this is the check data. Okay, so for every data item, we have two pieces of data. So we've just got an explosion in 2 in the total amount of data we're storing. If we have a public constant, you can kind of trivially share it by party 1 can take that constant v, everyone else takes xi equals 0, and we can have the MAC is just alpha I times v, and that will be correct. Okay, so simple, everyone get this, yeah? Good. Okay, now if we have a sharing like that, we'll call it square brackets x to denote that it's been shared with this MAC. And what the protocol is going to do is it's going to work in the pre-processing model. So imagine it's like a bank in that overnight you do shitloads of computation, and then during the day you actually want to process transactions. So you do lots of computation overnight, and then during the day you consume the data you've computed over the night as you do the computation during the day. Okay? So overnight, what I'm going to do is for some method, magic method, which I'll explain later, I compute sharings of A, B, and C such that we've got sharing of A, sharing of B, sharing of C, such that C equals A times B. And I produce millions of these overnight. Yeah? In a way I'll explain later. So just imagine these have just been given to you for free at the moment. Okay. So how are we going to do computation? So what we're going to do is we're going to represent the computation as what's called an arithmetic circuit over FP. So in other words, we express the computation as a sequence of multiplies and additions modulo p. Okay, now Computer Science 101 is we can do this because we can write everything down as a binary circuit, and we can take a binary circuit and we can write it out mod p. We can write it down as additions and multiplications mod p. So that's one way of doing it. Of course, there's more efficient ways because we can work with mod p. We can think of p as a 32-bit prime or a 64-bit prime, 128-bit prime, so we don't have to work with binary gates. And actually, it turns out we can do a lot more efficient stuff here. But for ease of exposition, I'll just assume we write everything down as a circuit. But that's not actually how you compute, because that's just stupid, yeah? But let's just assume, for ease of exposition, everything we can write down as a circuit, we know that, yeah? And so we have the function we want to compute, we express it as a circuit. And then we have the player's inputs, like my vote, okay? So what I do is I share my vote amongst the parties in a manner, which I won't explain how to do that, but that's easy. So just imagine we've got to the position where we have the function as a circuit, and the inputs of every player have already been shared in this way amongst all the players. So if we're going to evaluate the function, all we have to do is work out how to evaluate the circuit. And if the circuit just consists of addition and multiplication gates, all we have to work out is how to compute the addition and multiplication gates. Okay? It turns out addition is easy and multiplication is hard. Okay? So what we try to do is create a function which has as many additions as possible and try and reduce the number of multiplications. Essentially, every time we do a multiplication, we're going to have to do communication. So that's going to be a bottleneck.
I'm trying to estimate the number of orders of magnitude of inefficiency you've lost on each slide.
Okay, so far, I have, so I've lost an order of magnitude in one power of 2. A factor of 2 by this one, okay? So I just doubled the amount of data I have to store, okay? So if I want to solve 32-bit values or 64-bit values, I just have to hold an extra value per player. Okay, here I have to write everything out as a circuit, but this is a simplification. Okay, in the way we're kind of currently implementing stuff, we don't write things down as circuits. We write them down as programs which have operations, which we have special protocols to execute those operations. But for ease of exposition, we have a bit of a killer in this thing. So, and that's quite large, but it's polynomial, so theoretically it's okay. Okay.
I was waiting for you to say.
At the end of the talk, I'll give you some real numbers, and you can actually see what the difference is. Okay. So the more complicated. So what this does is that your usual notions of what's expensive computationally changes. Okay. So, but you'll see that'll come clearer when you see some numbers at the end. Okay. So we've got to add two numbers together. If we add two numbers, all we have to do is locally add our two values that we've got shared. So here we've only got, instead of having to do an add in the clear, if you were doing it clear, we now have to do two adds. So the explosion here in cost for Kevin's question is trivial. Okay, here. So addition is trivial in that we just locally add and we can add. And if you want to do the maths, the answer z is x plus y, because if we add up all the zi's, then it's just the adds of the xi's. It's kind of, yeah, it really is trivial. Okay, and then the max work because the max work. So addition is trivial. And essentially that addition works is because this secret sharing scheme is what's called a linear secret sharing scheme, is that when we secret share a value, we can compute any linear function of it for free. Okay? So if I have secret shared values x and y, and I have public constants v1, v2, v3, we can, with no communication and no extra cost, effectively compute any linear function. Okay? That's because everything's shared linearly. It's just linear algebra, yeah? So linear stuff is for free. Okay. And this is the trick we're going to use, that linear stuff is for free. Now, in what follows, which should be on the next slide, but there's not enough lines on the next slide, is that if we have a share x, when I say partially open a value, what I mean is I give away my sharing of that value. So if we go back to this slide, by partially opening the value, it means I reveal the xi, but I don't reveal the mac. I always have to keep the mac secret. And if you think about why I have to keep the mac secret, it's because if we all revealed our values shares of the mac, we'd all be able to compute this value, we'd know this value, and we could always, and then everyone could compute the secret key. And we want that secret key to always be secret. Yeah? So we never reveal the mac value. So what we're doing is when we say partially open a value, we reveal the xi, but not the gamma I. Okay? Everyone following so far? Yeah? Okay. Okay, so here's how you multiply, which looks really complicated, but it's actually really, really simple. Okay, so we're going to multiply a sharing of x with a sharing of y to get a sharing of z. So what we do is, remember that stuff we did overnight? We had these a, b's and c's. So we take one of those a, b's and c's off our list, and then I'm going to partially open x minus a. Okay. Now if we think about that, a is a random value, so x minus a is like a one-time pad of x. Yeah, so epsilon is a encryption, if you want, of the value x. So x has not been revealed. There's no information revealed from revealing epsilon. I partially open y minus b, let's call that rho, and by the same argument, b is like a random value, I've masked y with it, so this is like a one-time pad, and so there's no information in rho. And then I know epsilon now, I know rho, I know epsilon times rho, because I know epsilon, I know rho, so I just compute this linear function of z. and I can compute linear functions for free. Okay, so what we note is that every time I want to do a multiplication, I require interaction. I need to send 2 pieces of information out, and I need to receive 2 pieces of information from each player. So that seems we need order n squared communication, but you can tweak that so you get order n communication. Everything's a one-time pad. And we get the correct result by just this cool piece of maths. So let's suppose we were computing this thing in the clear. Well, we would compute C plus epsilon times B plus rho times A plus epsilon times rho. And then you just stick in what the epsilon and the rho are. There's epsilon, there's rho, there's epsilon, there's rho. And you expand it all out, and you notice everything cancels, and you just end up with x times y. So it's quite funky, yeah? It's a nice, funky little protocol for computing multiplications. But the killer is you require interaction. It turns out it's not the amount of data you send which is going to be your limiting factor, but it's actually the number of packets you have to send. So what you want to do is you want to amortize the number of rounds you do. So actually sending stuff is, actually the process of sending stuff is what takes time, not the amount of stuff you send. Okay. So that's how we evaluate the circuit. We can add by doing that, and we can multiply by doing that. Okay. And if we just did that, we would have a protocol that is passively secure. In other words, if we could guarantee that the adversaries always followed the protocol, we would be able to compute any function securely without revealing any information about the inputs. And as it stands, this protocol would be passively secure and would be better than the other solutions I talked about, the one by the Danish, the one by the SAP, the one by Estonia, and all the other ones that various academics have ever created. Okay? So on its own, this is just as efficient, if not more so, than the existing state of the art. But we want to protect against people cheating. And we're going to use the MACs to do that. So what we're going to do is interactively check the MAC values, which is as follows. So imagine that we've executed our protocol. We've got to the end. We've evaluated our circuit. Now, at some point, we've executed T multiplication gates. So there's been T partially open values, which we'll call AJ. And to each one of those, we've got an associated MAC value, yeah, where each player holds a share of that associated MAC value, and each player also holds a share of the MAC key. But we want to be able to check the MACs are correct without revealing the MAC key itself. And we do that once and for all at the very, very end of the computation, in that we generate some random values between us that we all agree on. We then just form a single value by adding up all the partial values. We form a single MAC share by adding up all the various MAC shares with those random values. And then we form the values sigma I. Each party forms sigma I, which is gamma I minus alpha I times A. We know that. We've just computed that. That's our combined share of the MAC. That's the global value we've just computed. And then we broadcast the sigma I's. And if all the computations are correct, then the sigma I's must add up to 0. So in other words, checking the computation at the end is effectively broadcasting of one thing. So if you compare that to previous methods where you had to do lots and lots of computation and communication at every multiplication gate, this is trivial. This just checks everything all in one go. And so we essentially get protection against malicious adversaries at effectively the same cost in running the protocol as if we were just protecting against passive adversaries. So protecting against malicious adversaries is just for free. Yeah?
They cheated the end then?
What's
From
that?
the last one to...
Okay, no, okay, you kind of, what you do is you commit then open.
Okay.
Yeah, so there's a kind of like, yeah, there's levels of indirect. Yeah, so you just kind of hash and then open the hash and whatever, yeah. Yeah. Yes, you have to make sure that when we say send, there's not the problem that who goes last has an advantage, yeah. Okay. So I kind of cheated in that one I said there was some pre-processing, and the other thing I've cheated in the sense that I haven't said this is just a multi-party computation protocol, and I've said that I'm going to make multi-party computation go much, much faster by using fully homomorphic encryption, which is meant to make things run slower, yeah? Okay, so I'm going to use something that makes things run slower to make something run fast, and I haven't told you how to do that. Well, the fully homomorphic encryption occurs in the overnight phase, this offline phase. And that's in where we compute the C, the A, and the B, these triples that we're going to consume. Okay. So the following is a naive version of what we're doing. You could actually scale it up very, this might look very inefficient, but when you actually implement it, this runs very, very fast. Okay, because you can do many, many computations at once, all in parallel with virtually no overhead. Okay, so a fully homomorphic encryption scheme, essentially, just basically, we can encrypt some message under some public key, gives us a ciphertext, encrypt some message under a public key, gives us another ciphertext, and if we decrypt the addition of the two ciphertexts, we get the addition of the messages, and if we decrypt the multiplication of the ciphertext, we get the multiplication of the messages. Okay. Now, the reason why our use of fully homomorphic encryption is going to be efficient is that we're not going to use fully homomorphic encryption. We're only going to be evaluating circuits using a homomorphic encryption scheme which have multiplicative depth 1. In other words, we allow as many additions as we want, but we only allow a single multiplication. Okay. So we're going to need a little bit more. What we're going to need is we're going to need a distributed decryption scheme for the fully homomorphic encryption. So every party is going to have a share of the secret key of the fully homomorphic encryption scheme, and that together they can together decrypt a ciphertext. Okay, this is easy to set up if you have shared RSA signing keys. It's roughly set up in the same way. Shared DSA signing keys, shared ELGA-MAL decryptions, shared RSA decryptions. It's roughly the same idea. So there's nothing really, it can be done, very easy to set up, so don't worry about that. And then how do we compute? So remember that key that everybody had, that share of the MAC key? So we just compute an encryption of the share of the MAC key at the beginning, and then we're completely done. And then if we've got this encryption of the share of the MAC key, that means everybody can compute an encryption of the MAC key because it's additively homomorphic. So I just add up all these ciphertexts, and by magic I get an encryption of alpha. Okay? Okay, so there's one protocol we need. Now this again looks slightly complicated, but if you go into detail, it's relatively straightforward. So I've got some ciphertext, and which encrypts a value m. And what I want is everybody in my protocol to obtain a share of that value. I want them all to get an MI such that the MIs sum up to m without knowing what m is. And I want to get, if needed, I want to create a new fresh ciphertext which encrypts m. So what I do is everybody just comes up with some random crap and encrypts it. Okay, and then just sends the random crap out. Okay, now let's imagine this random crap is fi, and f is the sum of the fi's. So I can create a ciphertext which encrypts m plus f by taking the ciphertext which encrypts m and adding to it all the ciphertext that everyone just individually created. Yeah? So that's a ciphertext which encrypts m plus f. Now what's f? F is just some random crap that everybody's produced because everybody's computed random crap and just added the crap together. So crap plus crap is crap. Okay? So now what I do is I decrypt the ciphertext which is m plus f to give me m plus f, surprisingly enough. And then party 1 can set his share m1 to be the value just obtained minus his random thing. Party I, not equal to 1, sets mi to be minus the random thing he came up with. And then if you notice that if you sum all those up together, you'll get m. So that's nice and simple. And we can create a new ciphertext by encrypting m plus f and subtracting this, where we use some sort of default randomness. And the reason for doing that is we want to keep restricting to multiplicative depth 1 circuit. So if we multiply, we then want to kind of bring keep creating fresh ciphertexts. Okay, so happy? Not happy? Happy? Vaguely? Okay. So here's how to generate A and B, given those components. Very simple. To generate A, you just generate some random AI. Everyone generates a random AI. You encrypt your random AI with the fully homomorphic encryption scheme. You add all the encryptions of AI together to get an encryption of A. You multiply the two things together to get an encryption of alpha times A. and then you execute the reshare protocol to get your sharing of the MAC. Yeah, because if you wanted to have a sharing, to get the shares of the MAC, you have to compute a sharing of alpha times A, so you just do the resharing. And you do the same to get B. Okay, so how am I going to compute how am I going to compute a sharing of C? I've got an encryption of A, encryption of B. Do exactly the same trick, exactly. So I've got the encryption of A, the encryption of B. I multiply them together. That gives me the encryption of C. I reshare it with my reshare protocol. That gives me my sharings of C. And then I can do the MAC in exactly the same way. Okay? And this is efficient. You know, every time when I execute one of these operations, I'm actually producing tens of thousands of these triples in one go. Yeah, with virtually no overhead. So I can produce millions and millions and millions overnight. Just keep churning, churning, churning. It's very, very simple. And we can produce we can do other stuff in the pre-processing phase, which I won't go into, because we're only going to imagine we're evaluating circuits. Okay. So that's basically the protocol. And that's called Speedz. It's called Speedz because it's me, Smart, Padro, Damgard, and Zacharias. And in Aarhus, they thought it would be much more fun to reorder the author name so it spelt out Speedz because it ran fast. Okay, so it's Speedz. There's another protocol called NNOS, which is very similar, but slightly different. But the point is, these are the two fastest protocols we have implementations for currently available, which are actively secure for any number of parties, from 2 upwards. The main thing is that the Speedz protocol works for working with arithmetic circuits modulo P, and NNOS is better for working with binary circuits. Okay, so specific functions you want to evaluate, some will be better with binary circuits, some will be better with arithmetic circuits. So you'd pick your protocol suite depending on which one is better. Okay. Both Speedz and NNOS are from this year's crypto. So the actual use of the creation of the protocols is from crypto, but since then there's been lots of implementation work. Okay, so what's the performance? What's the real numbers? Okay, so there's been lots of work in the literature about evaluating higher level functions than just addition and multiplication. So if you want to actually compute a higher level function, you don't actually you don't write the function down as a circuit and then evaluate the circuit. Yeah? If you want to do a comparison circuit, you don't write down the comparison circuit. You know, you actually do something slightly more intelligent. If you want to compute, we'll do a floating point operation, you don't actually execute the floating point thing, although it does take a while. Okay, you'll see in a minute. And what we have now is we have an ability, using the fully homomorphic encryption, to more function-independent stuff in the offline phase. In this pre-processing phase, we don't just have to produce these triples C, A, and B. We can produce anything we want, which will be in use for general computation later. So there's a lot of work we're doing at the moment trying to take stuff that you do in the online phase and move it to the offline phase for interesting functions like floating point operations, comparisons, etc. So in the next slide, you'll have one line which should, if you know anything about multi-party computation, the one line will impress you. And if you know nothing about multi-party computation, the other lines on the slide will make you laugh, okay, in the terms of the run times are very, very slow. But it'll give you an idea of what the current state of the art is. And when we, as I said, part of the issue is that when we send data along a network, it's not the amount of data we send which is the computational bottleneck, it's the fact that it's the number of times we send information. So what we do in our code is we apply lots of optimization algorithms to reduce the total number of rounds of communication. So we take an arbitrary program and then work out what the minimal number of rounds of communication there would be. Okay, so here's the numbers. Okay, so if we want to do a 32-bit integer multiplication, okay, we can do about 800,000 per second. That's about a 386. Okay, so that's the impressive line. We can compute.
Look at the age of people in this
Okay, well, yeah, that's a good question. 386. How many were born when there was a 386? Okay. So how many programmed a 386 or used a 386 at home? Okay, you could do stuff with it, yeah. So, okay, bar the explosion in writing everything down as an arithmetic circuit, we could securely evaluate a Pac-Man game, okay? So, or whatever else you did on a 386. So this is real computation, yeah? This is something useful. We could land someone on the moon securely, yeah? So this is real. Okay. The problem is that not all the functions that you're used to computing on a microprocessor are not necessarily that can be fast. So, okay, so the 32-bit integer multiplication, that is the timing after 4 months of aggressive optimization, right? Only 4 months. Okay, so we've aggressively optimized, throwing all sorts of bells and whistles at it. We can get that, and the latency is 0.001 of a second. Okay, so the other lines are timings produced by my PhD students the day before Christmas. So they probably weren't focusing too much on doing optimizations, and they probably only spent 2 or 3 days optimizing. But the hot off the press, or by Christmas holidays hot off the press, is to do a 32-bit integer comparison. So if you have values that we know are 32 bits long, to compare them, we can do 2,500 a second. Okay? Which is about 4,000, well, it's not even a 4004, because an Intel 4004 did 46,000 a second, okay? However, this 32-bit integer comparison, that's exactly what you need to do the auction application, yeah? So, or in some sense voting, yeah? You know, you add stuff up and then you do a comparison. So it's not actually that, you know, so you can imagine reasonable computations that you would want to do, but not searching your exabyte database. And then we have floating point operations. Okay, so weirdly, addition takes longer in floating point because you have to align the things. So you don't know how much you have to align, yeah? Because the exponent in the floating point value is secret. So you don't even know how much you, yeah, because it's a secret value, yes? You don't know how much you have to shift. But you can still do it, okay? And we can do about 50 ops per second. We implemented it and just did it, no optimization, okay? Or we could do 100 of multiplications. Multiplications are fine. And, okay, the ENIAC did 384 flops. Okay, so we can't even meet an ENIAC at the moment. Okay, so, but again, I reckon we should be able to get a factor of 100 by the summer. Okay, so I'm kind of, which is going to mean we're going to be faster than ENIAC, yeah. We'll probably be at EDSAC speed or whatever. Okay, my ENIAC timings are from there if you want to look up weird timings of microprocessors. Okay, so this is what Speedz can do at the moment. Okay, so that's for the large finite field. So when we do arithmetic circuits...
How much data is used in this?
4 months pre-computation.
No, not 4 months of pre-computation. This is for every integer multiplication I can do. I just consume an integer just 3 times as much stuff. So it's not really that much stuff being transferred. So to an 800,000, I'm transferring 1.6 million 32-bit values across the network. Okay.
These are 2 parties that are next to each other.
These are 2 parties on land. Or actually, what's interesting is we can scale this up for 10 parties, and we get very little difference.
In the same room.
In the same room. Yeah.
So as soon as you take someone out of the room,
the
speed of light kills you.
Yeah, that might kill you. Yeah, the internet will kill you. But the thing is that we compute stuff whilst we're waiting for stuff to come over the network. So we're not actually waiting. The protocols we've designed so we never wait. Yeah. So the real cost is actually sending the signal to the operating system, send this stuff, and then get the stuff back at the end. Okay. So if you actually wanted to compute over small finite fields, this is where you might want to either use a variant of Speedz, or you could use this NNOS protocol. So here what we do is we evaluate the AS function. So this is a very, very complicated function. And here we assume that the players have distributed the secret key. So we have a secret key shared amongst a set of players, and they want to compute a decryption or an encryption of an AS block. Okay. Now, this was done in the summer at Crypto using fully homomorphic encryption, and you could encrypt an AES block and it would take you a few days on a very, very large machine, 256 gigabyte RAM machine. Yeah, so this was not a desktop. Well, not a desktop these days. Okay. So the question is can we do something faster? And actually, it turns out that whilst it might take ages to compute a floating point operation, we can actually do with AES. We can get these kind of times. For Speedz, we can get 4 through per second at about a latency of 0.236. And with NNOS, we got a latency of 3 seconds, but in that time, we could do 33 at a time. And these are very, very, these implementations haven't been touched since the summer, and we reckon we get an order of magnitude improvement on these straight away, just by better programming, okay? So we reckon we can get a factor of 10 improvement instantly. So why would you care about evaluating AES? AES seems to be a stupid example to evaluate. Okay. Okay, so think of the following. There's been various attacks against, so this is where I'm going to end, so this was one application. So there's been various attacks against stored password systems, okay? So EMC RSA have a solution to this. And their solution works for static passwords in the following sense, is that when I want to log into a site with a static password, I XOR my password together into two things, P1 and P2. Now, now what I do as a user, I send P1 to server 1 and P2 to server 2. Now, the servers, they've got the password. They just want to compare the password, yeah? So what they do is they split P1. They've already got, they don't hold P, they hold a share of P. They hold P1 of S and P2 of S. Yeah? So what the EMC RSA solution is that how each server does, it just computes the XOR. And they send TI to each other, and then the servers just check whether T1 is equal to T2. And if T1 is equal to T2, then the user must have entered the right password. And the benefit of this is that for static passwords, you can't break into the, if you break into one server, you don't compromise the other thing. Now you can say, why the hell are you storing passwords in the clear anyway? But, but in some sense, the password has to go over the network. So if you've kind of sent one to one guy and one to the other guy, at no point, unless you break the channel communication between the 2 points, is the password ever there. So the password is only ever in existence in this system on the user's own machine. So even if you would then even if you had a system where you kind of encrypted the password to the server and the server then hashed it and then compared it to the password file, then this, you'd still have on the, if you broke into the server, you'd get the password, yeah? Okay, so so that's what their proposed solution is, but it only works for static passwords, which is kind of a bit silly because RSA actually make dynamic password things. Okay, so for dynamic passwords, what would you do? So here's the, so why would you have dynamic passwords? Well, you have dynamic passwords in secure ID tokens, which I haven't seen. Do you still have secure ID tokens in corporate America? I don't know. You do. Equivalent. Okay, so they still exist. Okay, so I haven't seen one for 15 years, but we see them all over the place in the. Oh, well, I have but I haven't used one. Okay, but we see them all over the place in Europe because we have EMV chip and PIN cards. Okay, which we use for e-banking applications. So whenever I connect to my online bank, I essentially create a one-time password with actually a DES encryption of some data that appears on some one-time system with my chip and PIN enabled credit card. Okay, so typically you could imagine that the password that you actually type in is the AES encryption under some master password of some nonce, either some value of some transaction if it's an e-banking or it's some counter or whatever, okay? So a dynamic password system kind of typically would look like AES encrypt under some secret which is stored on the server and by the user of some stuff that's known by everybody. And the idea is if you produce the valid AES ciphertext, then you have access to the system, okay? Okay, so here's something we're working on with Bar-Ilan and Partisia, which is the spin out in Denmark. So we propose a system to verify such dynamic passwords, and you need to compromise all the servers to break the system. And the solution is really simple. You just apply multi-party computation. Okay, and with the runtimes we have on this slide for AES, we just divide them by a factor of 10. That meets the actual requirements of people who do dynamic passwords in the real world. So we actually, with virtually, okay, they have to have a bit more iron at the back of their machines, but it's relatively straightforward to do. And we're actually working on a system to do this for real and extending it to DES, MD5-based passwords and SHA-1-based passwords and to get improved runtimes. So that's kind of why you might actually want to do AES functionality. I've actually seen a system which does, by another company, which does multi-party computation of AES decryption of emails. So you have an encrypted email that's AES encrypted. The key is transported with RSA. But you want to do searching of that email as it goes across the corporate boundary. So what you do is you put a gateway on the corporate boundary, which is divided into two or three servers, and you send a share of that key to each of the AES key to each of the servers. They decrypt the encrypted email, run the spam checker or whatever, the corporate policy on the email or on that thing securely. So they not only do the AES decryption of the email, but they also run the filter. Yeah, they express the filter as a finite state machine in a way that is suitable for multi-party computation. But because filters usually use if statements are a bit of a problem, because if I do a branch, I reveal which branch I do. So I actually have to write my filter in a way that is non-standard, in a way that doesn't involve branching computations. And that's actually possible, and it runs in real time. So you can send emails and it detects whether there's like secret mentioned in the email or other and blocks the email going through the gateway. The advantage here is that you've split the corporate gateway into three, so if you break one part of the corporate gateway, you don't reveal everything. Okay, so that's basically where we are. That's the state of the art in multi-party computation and FHE. Any questions?
Any questions? I have one. What allowed you to do AES so much more efficiently than that?
Okay, haha, right. So this is quite a good thing. In that originally we looked at AES because we thought that would be rather hard to compute because block ciphers, they're meant to be highly nonlinear and they're meant to be really hard to crypt and analyze. So they have very little mathematical structure. So let's look at AES. Turns out AES has huge amounts of mathematical structure, which enables it to be easily implemented with a multi-party computation. So AES is like designed as a block cipher that's efficient to evaluate in multi-party computation. I mean, so you're evaluating a function which is essentially of degree 2 to the 60. As if you think of it, if you expressed it as a circuit, it would be of degree 2 to the 60. But you can still evaluate it really, really efficiently because it's got so much mathematical structure. You just very trivial.
In a lot of statistical applications, I'm going to want to do floating point type stuff. Can you just talk about, I don't know, what's that going to look like? What does that look like now?
Okay, so statistical applications. So Microsoft, using FHE only, have a really cool demo where they do machine learning on two databases. So they have two databases which are encrypted with FHE. In real time, I think they take 5 seconds. I don't know how much their training data is. Yeah, so let's pick numbers off the top of my head. Suppose you have training data of 1,000 records in the database. They can do a cluster analysis to get the clustering data on the training data of 1,000 in about a minute, using just purely FHE, and then they can match things into the cluster. As they get new data in, they can put it into the right cluster. In also a matter of seconds. So they have, but this is again, it's particularly, what happens is that if you have a computation which has very, very low degree, it's very easy to evaluate. So it's the degree of the function you're evaluating that's complicated. So, and most statistical tests are linear or quadratic. Yeah, taking a mean is a linear operation. Means are trivial. Standard deviation, that's a quadratic operation, so that's trivial. If you think of most cluster stuff or most, like singular value decomposition, whatever, this is all matrix stuff. So this is kind of hit stuff with matrices. It's just quadratic. So we can, so we can compute relatively simple stuff. The real issue is can you come up with a high value enough application that doesn't have shitloads of data. The more data you have, it's going to kill you. So you actually have to there's a kind of sweet spot that you need to hit. But floating points, I mean, that's the real killer app. Once you can do floating point, you can do, yeah. There's lots of applications of floating point out there that's not necessarily database, but kind of, there's one to do with satellites hitting. You want to know? Yeah, or yeah, you can imagine, you've got coordinates and you want to kind of, people that things are traveling and you just want to run a two-body problem in computation, yeah, securely.
If you're willing to stipulate that your exponents are the same or near each other or something like that, do you end up getting
Yeah, that's the question I emailed my student like on the 4th of January, but he's on skiing holiday, so yeah. So what's called fixed point calculations, where we don't have the encrypted exponent, should run much faster, okay? But again, this is kind of, we expect those numbers to come out very, very soon. Yeah, but I would expect a few orders of magnitude. The fixed point calculations are much, much simpler. And also, it depends whether you want to be IEEE compliant as well.
Oh my.
So that floating point calculation is IEEE compliant. It actually executes the IEEE. Okay. So the issue is when you do a rounding, and to get the rounding in the correct order, if you're willing to pay a error in the rounding of 1 bit, so you either round up or round down, and then it runs much faster as well. So it depends, exactly what you mean by floating point. So again, you have to change your view of what you're computing. So that's the worst possible case for floating point: encrypted exponent and IEEE compliant.
Any other questions?
Do you see any applicability for non-revealing biometric?
Oh yes, so there's some Germans. So there's a huge number of applications out there. So some Germans have a working implementation of a two-party one, which does, we're using completely different technology, which does no-fly zone, no-fly lists. So if you have a picture on a no-fly list, and it matches the biometric information of the picture at the airport, so that the TSA, what's TSA? It's the right acronym, isn't it? Yeah, I don't know what it stands for, TSA, yeah. So the TSA have a no-fly list of faces, but they don't want to reveal what the no-fly list is, but you can just send the encrypted biometrics from their face. It can match against the database, and the people don't even know what face they're matching against the database. They just know whether it's yay or nay. Both parties learn whether it's yay or nay on the no-fly list without revealing the no-fly list and without revealing the person they're testing. And you could do that. If you can do that for faces, you can do it for fingerprints, you can do it for... but that's doable, but I'm not quite sure whether it scales. I mean, that's really academic test. I'm not quite sure whether that really does scale. You can get the throughput you need. But you don't need that much. I mean, there's only... Yeah.
So for something like that, as the database grows larger, is your performance degrading linearly?
comparisons?
Yeah, it's comparisons are the issue. So, but it's kind of, it should just scale linearly, because you're just saying you're not doing a binary search. You're just doing, you have to test against everyone anyway. The other, there's one, and so there's some people in America, Abby Shelat and some others have a system for just two-party computation. They can evaluate binary circuits at billions of gates per second. But again, it's a completely different model, and it only works for two parties and stuff. But you can, so these things are becoming much more realistic. Yeah, so the improvement is like 10 orders of magnitude within the last year. And so you can expect you'll have the orders of magnitude improvement going forward.
Okay, well, I think we should wrap up now. If there are any other questions, you can take them offline. Let's thank our speaker, though.